This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Welcome back to the WE Heraeus International Winter School on Gravity and Light. In this tutorial we will deal with the notion of connections. So, we start with exercise 1. It's a multiple choice question. These are multiple choice questions designed to spark discussion and as a self-test. We shall tick the correct statements, but not the incorrect ones. So, let's start with the first question. A covariant derivative operator, nabla x, is C-infinity linear in x. This statement is correct as it was shown in the lecture. A covariant derivative operator, nabla x, cannot be applied to 0,0 tensor field. This answer is wrong, as 0,0 tensor fields are just functions. And of course, you can apply a covariant derivative to a function. This is simply the action of x on f. So, the statement is wrong. The next one says that a covariant derivative operator acts simply as the partial derivative if the manifold is flat. So here one has to say what flat means. So a flat manifold is when we have introduced curvature, a manifold where curvature vanishes everywhere. This is equivalent to that there exist charts from an atlas that cover the whole manifold in which the connection coefficients vanish. However, that doesn't mean that in every chart the connection coefficients vanish. There can be charts, even on a flat manifold, where you have non-vanishing connection coefficient functions. And thus, a covariant derivative operator doesn't act as a partial derivative if the manifold is flat, and this statement is wrong. The fourth answer says a covariant derivative operator, nabla x, applied to a smooth function is the gradient of this function. Well, at first sight, this seems correct. However, we have nabla x acting on f is the gradient of the function applied to this vector x, and the gradient itself is only df, an element from the cotangent space. So this answer is wrong, as the covariant derivative operator applied to a smooth function is the gradient of this function applied to the vector field x. And the last statement says that a covariant derivative operator is uniquely fixed by choosing dim m to the power 3 many connection coefficient functions of an atlas. So this statement now is right, as we can choose the connection coefficient functions that carry 3 indices, a, b, c, that all run from 1 to dim m, and if we choose all of them, we have the action of this covariant derivative operator fixed uniquely. In the second part of this exercise, we again look at statements about connections. So, a connection maps a vector field and a PQ tensor field to the real numbers. This is wrong, as a connection maps a vector field and a PQ tensor field again to a PQ tensor field, but not to the real numbers. A connection satisfies the Leibniz rule. Yes, this is correct. This was one of the axioms presented in the lecture. Connection coefficients vanishing in a chart vanish in the overlap with another chart. This statement is not correct, so one looks at the transformation behavior of the connection coefficient functions, and at first this reads just like the transformation behavior of a tensor field. However, there's an additional term, del 2 x k, del yb, del yc, del ya, del xk, and this second term destroys the transformation behavior of a tensor field. So even if the connection coefficients, for example, vanish in this chart x, we still get non-vanishing connection coefficient functions in the overlap with the other chart y, as we have this additional term that is usually non-zero when changing charts. So this answer is wrong. The fourth answer says that the connection coefficient functions may be defined by nabla, the covariant derivative, and the chart-induced basis fields. Yes, this is correct, as we had that nabla of del xb applied on the chart-induced basis field del xc is the connection coefficient function gamma abc times del xa. And this defines the connection coefficient functions purely by the action of the nabla and the chart-induced basis fields. And the last statement is that a torsion-free connection has coefficient functions satisfying that lambda k and the antisymmetrized part of gamma k ab is 0 in all charts. So this is correct, as the torsion T that also carries indices A in above and BC in the bottom, and that is exactly gamma ABC minus gamma ACB. So the lower indices exchange, and that is exactly that we have the anti-symmetrization bracket at, or this is 2 times the anti-symmetrization bracket. So this is 2 times the gamma with the anti-symmetrization bracket. And if we have vanishing torsion, also this anti-symmetrized part of the connection coefficient function vanishes, and the statement is correct. So let's move on to exercise 2. Here we will look at some practical rules for how the covariant derivative nabla acts. So we'll see various examples of a covariant derivative acting on all kinds of tensor fields. So the first one is rather easy. The covariant derivative acts on a function, and this is just the action of the vector field on the function f, which can be written as in components xi dxi on f. Now in the next example we have the action of a covariant derivative on a vector field y, and we take the 8th component of the result. Again, the first term is just the action of the vector field x on y, and we can take the 8th component right away. But then we have to use the connection coefficient functions gamma to take an index a up here, and have BC down here with a component yb from the vector field y and xc from the vector field x. We can write out the first term again in components as xi del ya on del x yi del xi, and the second term just stays gamma a bc yb xc. After applying the covariant derivative to a vector, we apply it to a covector and take again the eighth component. So the first term is again x acting on the component omega a of the covector, but then we get a minus sign. We have an index m up here, an index a, and another index b, and down here we have omega m and xb as the both components going into this expression, and again we can write the first term in components, so component xi times del omega a after del xi, and the second term again stays the same. So we have understood how we can act with a covariant derivative on a vector as well as on a covector. So we can now look at a little bit more complicated example, namely the action on a 1-2 tensor field. So here we have that nabla m acts on a tensor, namely a 1-2 tensor. Let's first rewrite this a little bit. So this nabla m just means that we take the covariant derivative with respect to del xm on T, resulting in a 1-2 tensor field. So that is, we have del xm acting on the tensor field TABC, and then we get one term with the gammas with plus that takes care of this upper index here. So we get the index A here and indices BC down here. So the index C now is eliminated in favor of this M, and we get T, the tensor field T, that carries, now T was a bad choice here. Let's take N. So we have Tn here, and here we now have BC. So we have taken care of the upper index here, and now we get two terms with a minus sign that take care of the lower indices here. So we have minus gamma n. Here, down here we get a b, and again the m. And we have that tensor field T, A, here we get an index n and the C, and we get the same for the other index position. So n again, now we have the index C here, and again m, and the tensor field T, A, B, n. So this is the action of a covariant derivative on a 1-2 tensor field. In the next example we have that, again, a covariant derivative acts on a covector. However, now we have these antisymmetrization brackets here. So that makes it a little bit more complicated, however, not much. So we first expand these anti-symmetrization brackets. We get a factor of 1/2. Then we have nabla m a n minus nabla n acting on a m. Of course, we have to set the appropriate brackets here. And then we can use the results from above and write this out as 1/2. So we have del an by del xm minus gamma and index r up here. We have the index n here, m, and the AR. So that was the first term. Then from here goes into this one, and now we get the other term. So we have a minus del AM by del XN. Now we will get again a minus sign. However, as we have a minus sign here, we get a plus sign. We have a gamma R. Now we have M and N and AR. So we close the brackets. And now we see that we have here this term is equal or is nearly equal to this term. We have just a different sign before it, and here, down here, the index is the other way around. The index combination is the other way around. So we can write this again using our anti-symmetrization brackets. So we first write down these terms del A by del X, and then we can write those two terms here with an anti-symmetrization bracket as gamma R anti-symmetrized in M and N on AR. And now we know from the question up here that we have a torsion-free covariant derivative. That means, as we discussed in exercise 1, this antisymmetric part of the connection coefficient function vanishes. And thus we're left over with the expression 1/2 del AN del XM minus del AM by del XN. And now we can recognize this expression with a physical quantity, namely 1/2 times the electromagnetic tensor Fmn. So, this was already the second last example, and now we come to the last example. Again, we have an antisymmetrization bracket, but now containing 3 indices. So, again, the first step is to expand these antisymmetrization brackets. That is now a little more work. So we get a factor 1 over 3 factorial, as we have now 3 indices. Then we have nabla m acting on omega nr, and we get a minus sign with omega m acting on rn, as we have now exchanged the indices r and n, and as the whole expression is antisymmetric. That means if we exchange any two indices, we pick up a minus sign. So that's why we have a minus sign here. Then we also get the term that we have nabla n acting on omega mr and plus omega n, nabla n, acting on omega rm. And the last two terms are minus nabla r acting on omega nm and plus omega nabla r acting on omega mn. So we write this out, we get 1 over 6, and we get a del m. You don't get a del m, you get a del after del, so we get a del omega nr on del, by del xm minus gamma a n m omega a r minus gamma a r m on omega n a. The second term, this here, can be expanded to minus del omega rn on del x by del xm. We get now a plus, so we have a minus sign here. Again we have a rm omega an, and we get another plus sign omega a and m omega ra. And the other terms go similarly. We have minus del omega mr by del xn. Again a plus a. Now we get mn here. We have omega ar plus omega a rn on omega m a, and now on plus del omega rm by del xn minus gamma a rn omega am minus gamma a mn omega ra. And the last two terms, they read del omega nm by del xr. They get a plus sign a and r on omega am and plus omega a m r on omega na plus del omega m n by del xr minus gamma a m r omega a n minus gamma a n r omega m a. So these are a lot of terms. However, we now again use that this covariant derivative is torsion free, meaning we can kill terms that have different sign and the lower two indices exchanged here. So we can eliminate all antisymmetrized parts of the gammas. So we see now that this term and this term, they are antisymmetric to each other, so the indices are exchanged and they get a different minus sign, as well as the omega AR appears in both terms, so they go out against each other. You can also see that this term that contains omega and A and this term are antisymmetric to each other, so these two go out as well. This term containing omega AN appears down here again. They go out against each other. Omega RA is killed with this one just below. We have omega MA and omega MA in the last term here, so they go out. And the last two terms are those two. They go out as well. So what we are left with is only terms that contain such derivatives. Del omega Rn by del Xm minus del omega Mr on del Xn plus del omega Rm by del Xm, sorry, R at del Xn, and minus del omega Nm by del Xr plus del omega Mn by del Xr. And now we can reintroduce the antisymmetrization bracket, and what we get is that we have del by del Xm, where the m already is in the antisymmetrization bracket, and we have the nr at the omega also in the antisymmetrization bracket. And we see that even if we let a covariant derivative act on a 0 n tensor field, so this generalizes to even higher orders, not only 1 or 2 as shown here, but if we let a covariant derivative act on any 0 n tensor field and we take the antisymmetrized, or the fully antisymmetrized part of the result, all the connection coefficients will vanish and we're only left with terms containing these derivatives that take this form. Of course, this only holds if we have a torsion-free covariant derivative. So, that was exercise 2. Let's move on to exercise 3, where we will deal with connection coefficients. So the first question asks us to recall how the connection coefficient functions in a chart u intersected v, y are related to those in a chart with also the domain u intersected v, but now the chart map x. So the solution is just the transformation behavior of the connection coefficient functions, and it is given by the gamma in the chart y has components a, b, c, or has components that carry indices a, b, c, and that is we have del ya by del xm, del xn by del yb, del xr by del yc, and the gamma in the x chart with indices m, n, and r. But we get this additional term plus del 2xk by del yb, del yc, and del ya by del yxk. So this is the transformation behavior of the connection coefficient functions. They don't transform like a tensor, it's only the first part here, but they pick up another term here containing such a second derivative of the chart transition function. So the second question asks us, which class of chart transition maps make the connection coefficients appear to transform like a tensor? So we take a quick look back at the transformation behavior of the connection coefficient functions, which we wrote down here. So the first term is this part of the transformation that looks like as if the gammas were a tensor. However, the second part ruins it. So in order to make them look like transforming like a tensor, we need to have this second term vanishing. And that is only possible if we say that the second derivative of the chart transition map vanishes. And that we can achieve if we say that the chart transition map is a so-called affine map. So we have the chart transition map that takes d many real numbers from Rd, and we have a linear map Aij and A, and we have real numbers Aij. You can multiply it to Aj, and we can add some numbers Bj, Bi, so that we get the index right. So Aij so all the Aij's are real numbers, the beta i's are real numbers, and this is a so-called affine map. And you easily see that if you derive this chart transition map twice with respect to any entries, you will always get 0. And with this, we kill the second term up here in the transformation behavior of the connection coefficient functions, and thus make them look like transforming like a tensor. But of course, this is a very, very special choice of transition maps, and for arbitrary chart transition maps, this term will not vanish, and thus the connection coefficients don't transform like a tensor. So let's move on and look at an example. So we look at the flat plane. We consider two charts that both cover the upper half plane. That means we just take all points A, B from R2 that have the second entry larger than 0. One of these chart maps represents the familiar Cartesian coordinates, and the familiar polar coordinates are the other chart map. So we know that the chart transition map from Cartesian to polar coordinates is given by this expression, while the inverse transition map from polar to Cartesian coordinates is given by x after y inverse of r and phi is r cosine phi and r sine phi. Since we are on the upper half plane, we get r as an element from r plus, so positive real number, and phi is from the open interval from 0 to pi. We now start with the assumption that we have vanishing connection coefficients on the Cartesian chart, and we want to calculate the connection coefficients in the polar coordinate chart. So, recall that we have gamma A in the y chart BC is, so we make it easier, we look again at the transformation behavior up here. So now in our exam or in our questionnaire we have that all these connection coefficient functions in the Cartesian chart, they vanish. So this first term is gone, and we're only left with the second term. So we'll write this down again. It is del 2xk del yb del yc, and we're del ya by del xk. Very good. So now we have to look at how do these guys here, so this del ya by del xk look like, and how does this term here look like. So therefore, we will first look at the easier chart transition map, that is x after y inverse. So this is clearly easier than the other one, as it contains less terms and they're less complicated in general. And we look at expressions like del x m by del yn. We can rewrite this as del n on xm after y inverse, and so we, in the end, these connection coefficient functions, they shall be given in terms of r and phi, so the coordinates on the polar coordinate chart. And thus we already say that we want this expression here to be evaluated at y inverse of r and phi. So this object, sorry, this is not, of course, not evaluated at y inverse of r phi. So we see here that this is evaluated at y of, no, it's also not evaluated at y. No, it's just evaluated at r and phi, of course. But then it was correct that this is evaluated at y inverse of r and phi. So this is a linear map carrying an index up and down. So we can represent this in matrix form. So we take, so this is, we want to calculate the first, so the 1, 1 entry here. We take x1 of the y inverse, we derive it with respect to the first entry, and we evaluate at r and phi, and from the form up here we clearly see that we are left with cosine phi in this entry. So we say that m labels, the index m labels the rows of this matrix. So we get x1, so this entry here, derived with respect to the second entry, del 2x on x1 after y inverse, and we evaluate this at r and phi, and then we get minus r sine of phi here. Then we take now the second part, derive it with respect to the first entry, and we get a sine phi for this entry 2, 1 in our matrix, and the last entry is given by r cosine phi. Okay, so we have now calculated del xm after del yn, and now we have to look at the other way around. So this was transition map x after y inverse, but we have to also do it for y after x inverse, as we also have terms appearing that are of the form del ym after del xn. So this term is clearly evaluated at x inverse of a and b. So we need to rewrite this as del n on ym after x inverse. And now these numbers a, b are just the chart representative of x acting on some p in the flat plane in the manifold. So now we can insert the identity. We find that it's x inverse, x after y inverse after y of p. And now we know that y of p is just the chart, so it's just numbers in the chart. So we can write this as del n ym after x inverse on x after y inverse from some r and phi. So we have now here the other transition maps, as a transition map, y after x inverse. But now we evaluate this in terms of the variables r and phi from our polar coordinate chart. And that means that we don't have to calculate all the derivatives acting up here, but we can rather take this object here, this linear map, and take its inverse, and then we will end up at del ym after del xn. Okay, so we look at this object, del ym by del xn, evaluated at some x inverse of ab, so that's a point in the manifold, but we can look at this point equivalently through the chart y. So y inverse of r and phi comes here. And now we can just take the inverse of this matrix up here. I call it JMN for the moment, so the components are labeled by JMN. We can calculate the determinant. That's that J is R. It's quite obvious, as we have cosine phi times r cosine phi is r cosine squared. Here we get a plus, so minus times minus is plus, r sine squared, and that's just r. So we first have to take 1 over the determinant, and then we flip the diagonal entry, so we get r cosine phi here and cosine phi down here. The off-diagonal entries, they stay at their position, however they get the different sign. So we have here r sine phi, and here we get minus sine phi. And again, we label it with indices m and n. We can now check that, well, we may now check that this is indeed the inverse. And we will see, well, yes, it is. We get the identity back. So, and now we can start and calculate one connection coefficient. So we'll take gamma 1, 2, 2, for example. That is evaluated at y inverse of r and phi. So this is del 2 xk by del yb, del yc at y inverse of r and phi, and we have here del ya, del xk, so this is a k here, at y inverse of r and phi. So we can now plug in the indices correctly, so we get a del y1 here, and down here we get del y2, del y2. However, we still have the sum over k here, but we can quickly expand it in the corresponding terms. So we get one term that has x1, as well as we get one term with x2. So, and now we can plug in. So first look at del 2 x1 after del y2 del y2. So the basis therefore is the value of del x1 by del y2. So we have to go up here, del x1 by del y2 is this entry here. And now we have to derive it another time with respect to the second entry. And if we evaluate at r and phi, we will see that this is simply minus r cosine phi. And del y1 by del x1, well, this is easy, we just read it off. Here it is cosine phi. And here, in this term, again, del 2 x2 by del y2 del y2. So we look at del x2 del y2, that is this one here, r cosine phi. We derive it with respect to the second entry, and we get minus r sine phi, and y del y1 by del x2. Well, that's easy, we get just look at this entry here, that's sine phi, and what we end up with is that the result is minus r. So we have the connection coefficient function gamma 1, 2, 2 is minus r. So of course there are more connection coefficient functions, however we won't calculate them here. You can do this for yourself. So now we come to the last exercise, that's exercise 4, and we look at why on functions the covariant derivative nabla reduces to the usual d. So let's recall how x acts on a function h, which is a smooth function. So that's x of h, or equivalently that's the gradient of h applied to x. So question now is to complete the sketch of proof that is shown below for the scaling part of the C infinity linearity by one time indicating over each such S multiplication on which space it is defined, and giving sufficient such justification for each of these equal signs. So let's start. So the starting point is nabla of, with respect to some g times x acting on h. So this S multiplication here is defined on gamma of Tm, so to say the collection of all vector fields over M. Now we can apply the definition of a vector field acting on a covariant derivative with respect to a vector field acting on a function. So that's just definition. And we get that it is g times x acting on h. So still, this multiplication here is on gamma Tm, as we still multiply a function to a vector field. And now this equal sign here is the most critical one in this proof. Therefore, we have to evaluate the left side as well as the right side pointwise. So we have that it is g times x applied to h, and everything evaluated at a point P in the manifold, and due to the multiplication here on gamma Tm, we find that this is g of P, so that this is evaluated pointwise, g of P xh on P. So now this equal sign here lives on R, since we have real number here, a real number here. And now we can again pull the P out, and we get that this is g times xh, and the whole expression evaluated at some point P. And this multiplicative sign now lives on the smooth functions C infinity of m. So, it was already indicated that this multiplication now lives on the smooth functions. And now we have xh here, and we can plug in the definition of the covariant derivative acting on a function from up here. So this equal sign is justified just by definition, and still this multiplication happens on the smooth functions. And now we shall provide analogous proofs for the other axioms. So, we look at linearity in the vector fields here. So again, we first plug in, so of course this plus is also defined on gamma of Tm. As we add two vector fields, we plug in the definition of the covariant derivative acting on a function. So still this plus lives on gamma Tm. Now we can, and at this point again we have, or at this point we again have to look at pointwise evaluation of this expression, and again we find that due to the structure on Tm, on gamma Tm, that this has to be evaluated pointwise. So we have xh plus yh, and the whole expression evaluated at t at some point P. And due to that we have xh plus yh, where now this addition lives on the smooth functions, and we plug in the definition of the covariant derivative again, and we find that this is nabla x on h plus nabla y on h. Next point is to look at linearity in the argument here. So again, this addition is defined on the smooth functions. This equal sign is just here by definition. So we have x acting on h plus g. Still this addition is defined on the smooth functions. And now the same argument with pointwise evaluation holds, and we will find that this is xh plus xg, and that is just because of the definition nabla x on h plus nabla x on g. So we have linearity in the argument here. And the last part here, so it says that nabla x acts on the product f times g. So we again put in the definition. We find that this is x of f times g. And now we can save ourselves some work if we see that we can expand this into components. And now from the last tutorial on Friday, we know that this here is that for this expression a product rule holds, so we have del f del xi times g plus f del g by del xi. So we know that from the last tutorial, as we have already shown this, and we find that this is xi on dxi on f times g plus plus f times xi del g by del xi, and that is just x on f times g plus f times x on g, where this plus here is evaluated, it lives on the smooth functions as well as this one does. And this multiplication lives on the real numbers as well as this one does. So with this we finish this tutorial sheet about connections.